When you look at a photo, your brain instantly recognizes faces, objects, and scenes. But how do we teach a computer to do the same? Traditional neural networks fail spectacularly at this task. Feed a 1000 by 1000 pixel image into a fully connected network, and you're dealing with 1 million input neurons, each connected to every neuron in the next layer. That's billions of parameters just in the first layer. This is where convolutional neural networks revolutionized computer vision. CNNs don't treat images as flat lists of numbers. They preserve spatial structure, detect local patterns, and build hierarchical representations, just like your visual cortex. By 2012, AlexNet used CNNs to slash error rates on ImageNet by 41%. Today, CNNs power facial recognition, autonomous vehicles, medical diagnosis, and more. Let's build this from the ground up. Before convolutions, we need to understand what an image really is to a computer. A grayscale image is simply a 2D matrix where each cell contains a pixel intensity value between 0 black and 255 white. A 28 by 28 image like those in MNIST is a 28 by 28 matrix, 784 numbers. Color images add complexity. They're represented as 3 stacked matrices, red, green, and blue channels. Each channel is its own 2D matrix. A 224 by 224 RGB image is actually a tensor with shape 224 by 224 by 3. That's 150,528 numbers total. This numerical representation is crucial because it means we can apply mathematical operations to images, and that's exactly what convolution does. Convolution is a mathematical operation that combines 2 functions to produce a third. In image processing, we slide a small matrix called a kernel or filter across the input image, computing element-wise multiplication and summing the results at each position. Here's a concrete example. Take a 5 by 5 input image and a 3 by 3 kernel. Place the kernel at the top left corner. Multiply each kernel value by the corresponding image pixel beneath it. Sum all 9 products to get a single output value. Now slide the kernel 1 pixel to the right and repeat. Continue until you've covered the entire image. This sliding window operation is convolution. The output is called a feature map. It highlights specific patterns in the input. Different kernels detect different features. A vertical edge detector uses specific values. When this kernel slides over a vertical edge in the image, the left side multiplies dark pixels by -1, the right side multiplies bright pixels by +1. The sum becomes large, detecting the edge. Horizontal edges, diagonal edges, blurs, sharpening. Each requires a different kernel. The genius of CNNs? We don't manually design these kernels. The network learns them through training. A convolutional layer applies multiple filters to the input, producing multiple feature maps. If we use 32 filters on a grayscale input, we get 32 output channels, each detecting different patterns. Key parameters define this operation. Filter size, typically 3 by 3 or 5 by 5. Smaller filters capture fine details, larger filters capture broader patterns. Stride, how many pixels we move the filter each step. Stride 1 means sliding 1 pixel at a time. Stride 2 skips every other position, reducing output size. Padding, adding zeros around the input border. Same padding preserves input dimensions. Valid padding shrinks the output. Number of filters. More filters mean more features detected but more parameters to train. For a 28 by 28 input with 3 by 3 filters, stride 1, and padding 1, we get 28 by 28 output. Same size preserved. Each convolutional layer learns hierarchical features. Early layers detect edges and textures. Middle layers combine these into shapes and parts. Deep layers recognize complete objects. After convolution, we apply an activation function. ReLU, rectified linear unit, is the standard choice. ReLU sets all negative values to 0, keeping positive values unchanged. This introduces nonlinearity, allowing the network to learn complex patterns beyond simple linear combinations. Without activation functions, stacking multiple layers would be equivalent to a single linear transformation. Pooling reduces spatial dimensions while preserving important features. Max pooling takes the maximum value in each region, typically 2 by 2 windows with stride 2, cutting dimensions in half. A 28 by 28 feature map becomes 14 by 14 after max pooling. This serves multiple purposes. Dimensionality reduction. Fewer parameters mean faster computation and less overfitting. Translation invariance. Pooling makes the network less sensitive to exact pixel positions. A cat is still a cat whether it's centered or slightly shifted. Receptive field expansion. Each neuron in deeper layers sees a larger region of the original input. A complete CNN chains these components into a deep architecture. Let's build a classic example for MNIST digit classification. Input, 28 by 28 by 1 grayscale image. Conv layer 1, 32 filters, 3 by 3 kernels, ReLU activation gives output, 28 by 28 by 32. Max pool 1, 2 by 2 windows, stride 2 gives output 14 by 14 by 32. Conv layer 2, 64 filters, 3 by 3 kernels, ReLU activation gives output 14 by 14 by 64. Max pool 2, 2 by 2 windows, stride 2 gives output 7 by 7 by 64. Flatten, convert 7 by 7 by 64 tensor to 3136 element vector. Fully connected layer 1, 3136 to 128 neurons with ReLU activation. Fully connected layer 2, the output layer, 128 to 10 neurons with softmax activation. The softmax function converts final layer outputs into a probability distribution. Each output neuron represents the probability of a specific digit class. The network predicts digit 7 if the neuron at index 7 has the highest probability. Let's count parameters. Conv 1, 320 parameters. Conv 2, 18,496 parameters. Fully connected 1, 401,536 parameters. Fully connected 2, 1,290 parameters. Total, 421,642 trainable parameters. Compare this to a fully connected network on the same input with no spatial understanding. Training begins with a forward pass. Input images flow through the network, convolution operations extract features, pooling reduces dimensions, and fully connected layers output predictions. For a batch of images, we compute the loss function, typically categorical cross-entropy for classification. This measures how far predictions deviate from true labels. Lower loss means better performance. Here's where the magic happens. Healings. We use backpropagation to compute gradients, the partial derivative of the loss with respect to each parameter. The chain rule propagates error backward through the network. For convolutional layers, backpropagation is more complex than fully connected layers. We need gradients with respect to filter weights and input activations for the previous layer. The gradient of convolution with respect to filters is itself a convolution operation. This is why deep learning frameworks like PyTorch and TensorFlow are essential. They handle these computations automatically. Once we have gradients, we update parameters using an optimizer. Stochastic gradient descent is the foundation. Modern optimizers like Atom add momentum and adaptive learning rates for faster convergence. Training involves thousands of iterations. Feed forward a batch of images, calculate loss, backpropagate gradients, update parameters, repeat. We monitor validation accuracy to prevent overfitting. Early stopping halts training when validation performance stops improving. Our MNIST example is a toy network. Real-world CNNs are far deeper and more sophisticated. Linnet 5 in 1998, the pioneering CNN for digit recognition with 7 layers trained on MNIST. AlexNet in 2012, 5 convolutional layers, 3 fully connected layers, 60 million parameters, 1 ImageNet by a massive margin, proving CNN's power. VGGNet in 2014, very deep with 16 to 19 layers using only 3 by 3 filters. Simple, but effective architecture. ResNet in 2015 introduced residual connections, skip connections that allow gradients to flow through very deep networks up to 152 layers, solving the vanishing gradient problem. Inception or GoogleNet in 2014, parallel convolutional operations with different filter sizes combined in Inception modules, efficient and powerful. EfficientNet in 2019, compound scaling of depth, width, and resolution for optimal performance at various computational budgets. Key innovations include batch normalization, which normalizes activations between layers, stabilizing training, and allowing higher learning rates. Dropout randomly deactivates neurons during training to prevent overfitting. Data augmentation uses rotations, crops, flips, and color jittering to artificially expand training data. Transfer learning pre-trains on massive datasets like ImageNet, then fine-tunes on specific tasks with small datasets. CNNs have revolutionized computer vision. Medical imaging, detecting tumors in MRI scans, identifying diabetic retinopathy from retinal images, segmenting organs in CT scans. CNNs match or exceed human radiologist accuracy. Autonomous vehicles, real-time object detection for pedestrians, vehicles, traffic signs, and semantic segmentation identifying drivable road areas. Facial recognition, unlocking phones, security systems, social media photo tagging. FaceNet achieves 99.63% accuracy on the LFW benchmark. Content moderation, detecting inappropriate content on social platforms, identifying counterfeit products in e-commerce. Agriculture, crop disease detection from leaf images, yield prediction, automated harvesting. Industrial quality control, defect detection in manufacturing, visual inspection at scale. The same principles that detect edges in simple images now enable AI to see and understand the visual world. From pixels to insight, CNN's transformed computer vision.